This conference will now be recorded.
Hello everyone, we'll start with the problem. So this problem is based on the oxidation state which we have finished in the last class. The last slide in the last class was oxidation state. So based on this, we will solve this problem, and after that there will be discussion related to tendency of pi bond formation in case of group 14 elements, anomalous property of the first element of group 14 which is carbon, and chemical properties. Here the problem is related to germanium and lead. So it is saying that Ge2 compounds, that means germanium when it is in 2+ state, they are powerful reducing agent. Now if it is in 2+ state and it is mentioned powerful reducing agent, that means it can donate electron and it will be converted to Ge4+, so -2 electron. But when it is Pb, that is lead, now in +4 oxidation state, that means Pb4+, it is strong oxidant. That means it will have a tendency to accept electron and ultimately it will be converted to Pb2+. So these two, that is informations that are given in the question. Now it can be due to, what is the reason behind this type of observation for germanium and lead, that we have to find. So here the first option is saying that Pb is more electropositive than Ge. Now see here oxidation states are mentioned 2+, 4+, but Pb in 0 oxidation state and germanium in 0 oxidation state, whether it is more electropositive or not, it is not having any direct relationship. Then ionization potential of Pb less than that of Ge. Here also, when which ionization potential is not mentioned, that is first, second, whatever, then by default we consider the first. Now first ionization energy for Pb and germanium, that is also will not help us to answer this question. That is to give the explanation why we are having this type of observation. Basically observation information is given, we have to find the reason behind it, but this cannot be correct reason. Then ionic radii of lead 2+, 4+, they are larger than those of Ge2+, Ge4+. That means Pb2+ is larger than Ge2+ and Pb4+ larger than Ge4+. Again, whether ionic radii is large or not, how it is related to the oxidizing property and reducing property. So oxidizing property, as we are seeing here for Pb4+, that means Pb2+, it is more stable compared to Pb4+. And for the first observation, we can say that Ge2+, it is less stable than Ge4+. So that is why ultimately it is converted to Ge4+. Now why Pb2+ is more stable and why Ge4+ is more stable? To answer this question, basically we have to consider inert pair effect. So inert pair effect for group 14 elements which is having general electronic configuration NH2 NP2. So in NS, so for Ge and Pb, N value will differ, but in general we are considering. So this is NH2 NP2. Now 4+ oxidation state stable means what? That this pair of electron that you are seeing in NH2, it has to be in unpaired state. Then only it will be in this position. Sorry. Then it will be in this position and we can have that these 4 electrons can be removed and we will have Pb4+ or Ge4+. Now as we know that Ge and Pb, if you consider, after germanium there is also teen, that means Pb is below Ge, and as we move down the 2+ oxidation state becomes more stable, than 4+. Why? And this is because of inert pair effect. So as 2+ state is more stable than 4+, as we are moving down the group, that means Pb4+ will be less stable than Pb2+ because Pb is below Ge, and among these three basically Pb is more stable in 2+ state because of inert pair effect. Maximum the 2 electrons present in Np2 in case of Pb can be used for bond formation, but not the NH2 pair we can easily break because of inert pair effect. So that is why this is the correct option. That is, inert pair effect in case of lead is more pronounced compared to germanium, and that is the reason Pb2 plus will prefer, lead will prefer 2 plus state and germanium will prefer 4 plus state. Okay. So next we will start the actual topics. So tendency to form pi bonds for all the elements of group 14. Now the first element, let me write all the elements. Tin, lead. The first element, carbon, it has strong tendency to form p-pi multiple bonds. Now see, it is not just with itself. So it can form multiple bond with itself. That means another carbon atom, and multiple bond means the first bond is obviously sigma bond, and the extra bonds that you are seeing in double bond or triple bond, these extra bonds are pi bonds. So when there is CC double bond like this, then this is sigma, this is pi. When there is triple bond, this is sigma, these two are pi. Okay. Now not just with itself, but it can also form pi bond with oxygen, with sulfur, with nitrogen. Okay. So this type of multiple bond formation tendency or p-pi bond formation tendency with itself or other elements, this tendency is maximum for carbon. Okay. As now we are moving down the group starting from carbon until Pb, gradually this ability to form p-pi multiple bond, that ability will decrease. And why it is so? Because when you are moving down the group, the p orbital that will be involved, the size is increasing. So when it is carbon, it is 2p. When it is silicon, it is 3p, and gradually it will increase. Now when the size of p orbital is very large, it is very diffused. And because of this diffuse nature, suppose here between two p orbital, when pi bond formation is taking place, that is sidewise overlap, because of the compact nature and small size of 2p orbital, this type of sidewise overlap is good. But suppose 2-3p orbitals are involved, just like CC double bond, if you consider silicon double bond, then another silicon, then there should be pi bond between 2-3p. Now as here the size is increasing, it is more diffused. So that is why this type of sidewise overlap, it will not be very effective. So that is why when size is very small, mostly in second period, because 2p orbital is involved only, and if it is having high electronegativity, then also it will help in pi bond formation. So down the group, this tendency is decreasing. So heavier elements, they do not form p-pi bonds because their atomic orbitals are now very large and diffuse in nature. So effective overlapping like carbon, where 2p is involved, this is not possible. In case of silicon, that is the next element after carbon, and other heavier elements of this group, they can form d-pi bonds, and that is possible because they are having vacant d orbital. So in case of silicon, there is presence of 3d, here we have presence of 4d. So because of this vacant 3d or 4d, it can form d-pi bond with another element. So this d, it will be coming from the group 14 element, and the p orbital, that will be coming from another element. But they can use vacant d orbital for d-pi, which is obviously not possible in carbon because there is no d orbital present in second period. Now this tendency is particularly strong in case of silicon when it is linked to oxygen. So silicon linked to oxygen, so it will use 3d orbital, and oxygen, it will use 2p orbital. So there is d-pi bond formation is possible. So why it will prefer oxygen and nitrogen? Because oxygen, nitrogen, they are from second period, their electronegativity is very high. So this type of conditions are good for pi bond formation. So silicon linked to oxygen and nitrogen forming d-pi bond, where d is coming from silicon and p orbital is coming from oxygen and nitrogen. This type of bond formation is better. Okay. So that is all about the pi bond formation tendency in case of group 14 elements. So some CC double bond or CC triple bond example you can easily see in case of alkene, that is CC double bond. You have seen CC triple bond in case of alkynes. Then C double bond, that is carbonyl compound, for example. You can consider acetone, CH3, COCH3. Then cyanide, suppose I am writing here CH3, C triple bond N, that is methyl cyanide. Then C double bond S, that you can find in carbon sulfide. So these are some examples where you can see multiple bond formation by carbon, not just with itself but with other elements also, like nitrogen, oxygen, sulfur. Anomalous behavior of carbon. As we know, the first member of any group, we have already seen it for in S block elements, we have seen it for the first element. So when it is group 1, the first element we have seen lithium, and when it is group 2, the first element beryllium, we have seen how it is behaving differently for them from the rest of the members. In case of group 13, that is in P block element in this chapter, the first element is boron, which is behaving differently from the other members. Same thing now we will see for carbon. Carbon is having higher melting point, boiling point compared to other members. And why it is so? Because it has a tendency to form a structure where infinite network of very strong covalent bonds are present, and mostly these bonds are CC bonds. Now immediately if we are having problem to understand this, it will be clear when we will see the structure of different allotropes of carbon, like graphite, carbon. There you will be able to see this type of very large network structure where many strong covalent bonds, that is CC bonds, are present. Now why we are talking about strong bonds? Because melting point, boiling point is high for carbon, and it is high because of this type of strong covalent bond. So when we want to melt it, obviously we have to break the bond. When we want to boil it, we have to break these bonds. Okay. So to break these bonds, it's required very high amount of energy, and that is the reason why carbon is having higher melting point and boiling point if you compare with other members. Then carbon can show maximum covalency 4, and that reason is very clear because the same type of thing we have also seen for boron. There is no presence of d orbital, so maximum covalence is 4, because again if we consider NH2 NP2 configuration, and if you unpair the electron in NS, so this will be the placement of the 4 electrons in NS and NP. Now for carbon it is 2s and 2p, so it will be able to use these 4 orbitals for bond formation, but there is no d, so further enhancement of covalency is not possible. Okay, here you can see some examples where the central atom, what I mean by central atom, silicon in SiF6 2 negative charge, then germanium 6 chloride 2 negative, SnOH whole 6 2 negative. So the atoms I am marking, these are basically group 14 elements, silicon, germanium, tin, then lead. So here one thing is common, all are forming hexa coordinated complex, right? And all these elements, they are from group 14. So here you will not be able to see carbon because 6 coordination surrounding the central atom. Central atom is group 14 elements. This is not possible for carbon. And here the central atom is sp3d2. So just take any of the central atom, and if I consider, just take Sn. So when it is Sn, there is 5s2 5s2 5p2 configuration. Now this 5s2 5p2 configuration, this is 5s, this is 5p, and after that there is also presence of d orbitals. So it can use d orbital for hybridization. Now as it is mentioned that hybridization for each of the central atom is sp3d2. So from the these total numbers, if you consider 1s, 3p and 2d, that means total 6 coordination. So when there is sp3d2, this type of hybridization is going on. right? And here oxidation state is total 6 HO minus 2 negative charge extra. That means here oxidation state is 4 plus. So none of the electrons will be there. So all these orbitals, that is, there will be total 6 sp3d2 orbitals where HO minus will donate electrons. So here you can understand that because of the involvement of d orbital, we can have 6 coordination, which is not possible in case of carbon. Fine. And again, multiple bond formation, which we have just seen in the previous slide. So carbon is basically having the maximum tendency for pp bond formation, and it is because of its small size, because it belongs to second period, and its electronegativity is very high, which is these are the conditions for perfect pp multiple bond formation. So 2p overlap is very effective because its size is small. So these are the different factors by which carbon is behaving differently. Melting point, boiling point high, covalency limited to number 4, but for others it can be extended to 6, and pi bond formation tendency is maximum for carbon. So these are the features based on which carbon is showing anomalous behavior when compared to other members of the same group. Now, anomalous behavior, when we are talking about, the most important factor is catenation. So catenation is actually a property. Now, this property is maximum in case of carbon, and because of which it can form a very large network of type of structure. But what is catenation? Catenation is ability of like atoms. That means same atoms will link with another same atom. So suppose the atom is X. So it will link with another X like this. Okay. So like atoms, that is same atoms, to link with one another, and it is obviously through covalent bonds. Now, when we can expect catenation property, what are the necessary conditions to show this property? So these are: the valency of the element is greater than or equal to 2. So it has to be greater than 2. So you cannot expect it in case of group 1 or group 2, where valency is 1 and 2, right? Element should have the ability to bond with itself. So this type of bond with, that is between like atoms, that we can see in case of group 14. So this condition is also present, and maximum for carbon obviously. Then cell bond must be as strong as its bonds with other elements. So just think about carbon. It can form bond with carbon, with oxygen, with nitrogen. So in all these cases, the bonds are strong. So it is not that the cell bond, that is CC bond, it is strong, but the other bonds are with other elements, that should be also strong. Kinetic inertness of these catenated compounds toward other molecules. So once the catenated compound is formed, where there is bond between like atoms, okay, so they will show kinetic inertness. That means kinetic inertness means it will not have a tendency to react with other compounds immediately. So kinetics means how fast it is occurring. It is not thermodynamically inert. So if you change the condition, suppose you are increasing the temperature, then maybe it will be fast. But under normal condition, that is if you consider kinetics, how fast it will react, so that is not present. It is inert, kinetically inert to other compounds. So it is another way of saying that once the catenated compounds are formed, they will be very stable. That means these bonds are very strong. So it will not show so much reactivity to other compounds. So these are the conditions must be present for an element if it has to show catenation. Now carbon is such an element where all these properties are fulfilled. Not properties, I mean all these conditions are fulfilled. So that is why catenation is very high in case of carbon. And this is the reason mostly in organic chemistry you have seen long straight chain of carbon like this, then branch chain of carbon, okay, Then we have seen rings of different sizes and shapes. Just take the structure of cyclohexane or benzene. So these are very common in organic chemistry. So why carbon can form compounds like this? Branch chain, long chain, ring, different size, different shape. It is because of this catenation property. Now down the group, they will also show catenation, but not like carbon. So if you consider the EE bond, where E is any group 14 element, what happens? The bond energy, that is EE bond, it may be carbon-carbon bond, it may be silicon-silicon bond, because we are talking about like atom bond. Okay, then it may be GEG. So if you consider the bond strength, that is bond energy decreases rapidly, and as bond energies are decreasing down the group, that will lead to decrease in catenation. So the order of showing the catenation property, see carbon, after that silicon. But see, if you compare carbon and silicon, it is much greater than silicon. Then silicon having more tendency than the next element, germanium, and then germanium and tin almost same catenation, and these are again much higher than lead. So basically in case of lead, you will not see any catenation. So this is the only element in group 14 where catenation is not possible, but in other cases catenation is found, but maximum is in case of carbon. Now why this type of catenation property is decreasing down the group? It is directly related to the bond energy. So just have a look in the bond energy. When you are moving down the group, gradually the bond energy in kilojoule per mole, gradually it is decreasing, right? So this is the reason why it is decreasing. Now, because of the property of catenation and pi-pi bond formation, carbon has maximum tendency to form allotropic forms. Now, allotropic forms, we will discuss it once we have finished the chemical properties. But remember, what are allotropes? Allotropes are basically different type of structure of the same element within same physical state. What I mean to say by within same physical state, so just take carbon. It can show that is its allotropy is very high. It has different types of allotropic forms. Now within same physical state, that means all the allotropic forms, they are solid. It is not that their physical states are different. Physical state is same, but their structures, bonding, all these are different. And because of these difference, physical properties also different, but chemical properties are same. So just take carbon, very common allotropes are, that is the common example we give always, diamond and graphite. So both are solid, but their bond formation and structure, everything is different. But they will show the property of carbon, obviously, chemically if you consider, but their physical properties, melting point, boiling point, all these will not be same. So why it shows maximum allotropy property? It is also because of this catenation property and also this pi bond formation tendency, because both these are maximum in case of carbon, which is leading to maximum allotropic forms in case of carbon. Okay. Now based on this, here we have problem. The correct order of bond enthalpy kilojoule per mole unit for, if you look at the options, you will see all are group 14 elements, right? Now it is very easy to remember because in the previous slide just you have seen that there is smooth decrease down the group for these 4 elements, right? So that means it should be first carbon, then silicon, then germanium, then tin, and that is matching with option 4. It is quite easy. Now in this problem, at a first glance it may seem that why we have nitrogen element, because that belongs to group 15, but actually if you look at these two compounds, what is the difference? The difference is in this position. Here we have SiH3 whole 3N, that means 3 SiH3 groups. 3 SiH3 groups will be attached to nitrogen. But for CH3 whole 3, 3 CH3 group. So what is the difference? The difference is in the first compound we have silicon, in the second compound we have carbon. And carbon and silicon both are group 14 elements. So we have to find correct statement. So it is saying the first one, that is SiH3 whole 3n, planar, pyramidal, pyramidal, planar. So any one will be correct. And the second part of these statements for all these 4 options, it is saying that more basic than the other compound. This is also more basic. Then the next 2 options, less basic, less basic. Now basicity means what? Central atom is nitrogen, and we know there is lone pair over nitrogen. That means when lone pair donating, this lone pair donating tendency, it is high, then only we can say that it will be more basic. Now why that is initially if you are thinking that in both cases there will be lone pair over nitrogen, what is the problem? But see, what is the difference between carbon and silicon? In case of carbon, we have no d orbital, but when it is silicon, there is presence of vacant 3d orbital. And remember, in the first slide, that is the pi bond formation tendency, there we have one point where it is mentioned that silicon have a tendency for d pi p pi bond formation with nitrogen and oxygen. Now here we have nitrogen silicon bond. So you can expect d pi p pi bond formation between nitrogen and silicon, where 3d is coming from silicon and 2p is coming from nitrogen. Now when it is happening, then this lone pair will be donated towards the vacant d orbital of silicon. So there will be extra bond between nitrogen and silicon, and the lone pair donating tendency that will decrease. See, you look at this picture. Here the first compound is SiH3 whole 3n, and this is Me3n. Here the structure is with, that is if you do not consider if you consider the lone pair, that is total 4 positions, it is tetrahedral and sp3 hybridization, right? Total 4 position, angle is around 1090, it is sp3. But in this case the structure is planar. Why it is planar? Because there is some bond, pi bond between nitrogen and silicon, and this is also possible with other silicon nitrogen bonds. The average structure we can draw like this. Average structure, it will be, I'm drawing a dotted line for these 3 bonds. So it will be the average structure and it is planar. So see, not just planarity or more basic, here you can get also some other information. So what are the informations we are getting? First of all, it is planar. Second point, it is sp2. Then come this side, it is sp3 and it is tetrahedral. Okay, if you omit this part, it is pyramidal. That is only this part, if you consider, it is pyramidal. But sp3, this is sp2. The first compound is less basic because it is there is the lone pair from nitrogen, it is donated towards silicon. So the availability of lone pair over nitrogen is not so high as you can expect for the second compound. And one more information I will give here, though it is not required to solve this problem. So we have already got our answer, this one. It is planar, it is less basic. But how it will react with some acid? So if you consider Me3n and take HCl acid common, so this lone pair, it will be capturing this hydrogen, and after all the structure will be like this, Me3n plus HCl minus. But if the same reaction we are doing with NSiH3 whole 3, then what happens? So in this case, if you treat it with HCl, now what will happen? The Cl minus which is present in HCl, it will attack silicon, not nitrogen. And when it is attacking, this N-Si bond will be broken and the H will come to nitrogen. So what we are getting? We are getting SiH3 whole to NH. Now in this way, 2 more HCl can react, and ultimately these two SiH3 that will also be replaced by H. So after all, there will be ammonia and SiH3Cl, or better you write H3SiCl. So we are getting here ammonia and H3SiCl. So overall reaction, if we write this ammonia, it will react with another HCl. Ultimately, it will form NH4HCl. So see how many HCl are involved. For one molecule of this molecule, total 4 HCl. 1, 2, and then one more. So this is number 3. So the overall reaction, it will be 4 HCl plus SiH3 whole 3N, and it will produce ultimately NH4Cl, and there will be total total 3 H3SiC. So this is the overall balanced equation. So how it will behave with acid, that you can see in this equation. But correct option is last one. It is planar and less basic. Planar and also sp2 hybridized. Remember, correct order of melting point of group 14 elements. So melting point we have discussed in previous class, not in today's class. So here if we see the green line, that is for boiling point, and this line, this is for melting point. So melting point normally decreases, that is both melting point, boiling point decreases down the group, but we have some discrepancies. See, for carbon it is always very high, whether it is boiling point or melting point, both are very high. Then down the group it is decreasing, and only discrepancy you will find between Sn and Pb. Up to Sn it is smooth decrease, though the jumps are the gap between Sc and Si, it is very high. So maximum is carbon. So these two are not correct. Maximum is carbon. After that it is silicon, then it is germanium, then it is Pb. Okay, not Sn. So after germanium, which is greater than tin, now tin, it is not greater than Pb. See, it is greater for Pb. So that is why this should be the correct option. Okay, so the discrepancies between tin and lead. The correct order of catenation property. So we have just discussed catenation. So maximum is for carbon. Then let me write all the elements: germanium, tin, and Pb. So here it is max. After that it should be silicon. So after carbon it should be silicon, and for these two it is almost same, and Pb is not there because here you do not have any catenation. Okay, so there is no catenation. These two are almost same. Then carbon is greater than Si. So carbon, after that there is tin. So these two obviously not correct because carbon is maximum. But why A is cancelled? Because after carbon it is silicon, not tin. So this should be the correct option. Fine. Chemical properties. Reaction with oxygen. So group 14 elements, how they react with oxygen, that is we are going to discuss. They can form two types of oxide. One is monooxide, but the formula is EO, because see, it can show two. They can show two types of oxidation states. So when it is +2, the formula will be EO, where E is all the elements. When it is +4, now it will be EO2, because per oxygen there is 2 negative charge. So when it is +4 state, we need 2 oxide. Okay. So either monooxide or dioxide. Now under EO category, that is monooxide, if you consider silicon oxide, it is formed by the reduction of SiO2 with Si. It is true that when these elements are heated with oxygen, we get EO or EO2, but for silicon oxide, that is the monooxide type, it can also be formed by reducing SiO2. So SiO2, it is EO2 type. So this is EO type. So why we are calling it reduction? Because here oxidation state of silicon is +4 and we are treating it with silicon which is zero oxidation state. So when it will act as a reducing agent, and here from +4 state, now it is converted to +2. So that is why we are saying that reduction of SiO2. So SiO2 plus Si, we are getting 2SiO. In case of lead, though we have said that we have these two types of oxide, but for lead especially, we have a different types of oxide also. And it is called tri-lead tetroxide. Look at the formula, Pb3O4. Now here, if you look at the formula, and if you try to guess the oxidation state, total 4 oxide, that means total negative charge -8. Then is it that per Pb, the oxidation state is 8/3? Actually, that is not the case. Here we have two different types of oxidation state of lead, and that you will understand once you see its structure. So this is the structure. Here we have two different types of lead. That is, lead is present in two different chemical environment. If you consider the terminal lead, it is +2 oxidation state. The middle one is 4 oxidation state. Now this compound, it is mainly written as 2PbO dot PbO2. So how we are getting it? Suppose if you consider these two parts as if it is PbO with 2 plus state, and this part is PbO2. Okay, it is called red lead or minium. It is obtained, that is how we can prepare it. It is obtained by heating lead, that is monoxide PbO, with excess air or oxygen, temperature 673 Kelvin. So 6 PbO reacting with 1 O2, we are getting 2 Pb3O4. Tri-lead tetroxide, Pb3O4. It is also reddish orange color. Now for carbon, though we have said that two different types of oxide, monoxide EO and dioxide EO2, but there are some exceptions also. So these two oxides are common that you can expect for all the elements, but there are some exceptional cases. So one you have just seen for lead, and for carbon it can form few oxides that have no analog in Si or Ge. So one example you can give C3O2. So this type of oxide is also formed in case of in case of carbon. Okay, so this is unusual. You will not see it in case of germanium or silicon. Now come to the next two elements, that is for silicon and germanium. It will have no tendency to participate in pi-pi bond formation. We have already seen that this type of pi-pi bond formation, it is maximum in case of carbon. But this type of bond formation, it is not so high when you consider silicon, germanium. There is no such pi-pi bond formation tendency. So as a result, what happens? But +4 oxidation state is observed for them. So they has to satisfy tetravalency. But still there is no pi-pi bond formation. So for carbon, tetravalency can be fulfilled because carbon can form CO2 like this, tetravalency. See, 2 pi bonds are there like this. Then see, if you consider C3O2 structure, here also pi bond formation is there. So just both side of carbon there is pi bond, but this type of structure you cannot get for Si and Ge because down the group pi bond formation tendency becomes less. but they have to satisfy tetravalency. So, and also the bivalency of oxygen. So what they will do, they will undergo polymerization, forming this type of polymer. See, SiO2 whole N, GeO2 whole N, where N is very large number. So the structure which will be, that is extended structure, because there is no pi bond, but Si bond, then this oxygen, it will be linked to another silicon. So this is polymeric large structure, and it will be, why? Because tetravalency we have to satisfy for these two elements, but pi bond formation not possible. So that is why they are forming this type of polymer structure. Okay. So next we will see what about reaction with water. So when they are reacting with water, the first three elements, that is carbon, silicon, germanium, there is no reaction with water. Come to the fourth element. Let me write the elements again. So you have to know this sequence when you are moving down. Otherwise, whatever discussion here we are having, it will be difficult to understand. Okay. So carbon, silicon, germanium, they are the first three members, no effect with water. Then tin, the fourth compound, now with steam, that means high temperature, not room temperature water. With steam, it will form dioxide. So tin from 0 state, now it is +4 state, and hydrogen gas is there. Water for the next element lead, it will have no effect because of formation of a protective oxide film of lead oxide. So it will be acting as a protective layer. So though the reaction can start, but because of this layer, ultimately it will not be able to come into contact with water or steam, and there will be no reaction. Okay. Reaction with halogens. So when they react with halogens, there is two types of halides. Just in case of oxide, you have seen there is two types. One is EO, another one is EO2. Now when it is +2 state, in case of halides, it will form halide like EX2, that is the formula. But when it is having +4 oxidation state, now the formula is EX4. Except carbon, all other members react directly with halogens. So carbon, it will not react directly with halogens, but other members, under suitable condition, they can directly react with halogens. Now here we have this compound which is lead with that is EX4 type, but which X? Iodine, that is iodide. So lead tetraiodide, it is actually not existing. Why it doesn't exist? Because this lead iodine bond, even if it is formed initially during the reaction, it will not release enough energy so that 6s2 electrons can be unpaired. If you consider the electronic configuration of lead, it is 6s2 6p2. Now if it has to form PbI4, that means this electron we have to unpair. Now after unpairing, we are writing it like this. Now for unpairing this 6s2 electron, we need some energy. Now this energy we can get if PbI4 is formed. Now in PbI4 there will be total 4 lead iodine bond. So this bond formation, when the bond will be formed, some energy will be released, and that energy will be actually be used to unpair the 6s2 electrons. But the bond energy of 4 lead iodine bonds, these are not enough to unpair this 6s2 electron, because we know because of inner pair effect, this pair is having a inner tendency. So that is, to make it unpair, it is really difficult process. So this energy for 4 PbI bond formation, the energy that will be released, that is not enough to unpair this electron of lead and excite one of them to 6p. So see here I have already written it in 6p. So not just unpairing, we also have to shift it to 6p. For that also we need energy. But for these two process, the energy that we require, that we are not getting for the bond formation of 4 lead iodine bonds, and that is why this compound, even if it is formed, ultimately it will not be very stable, and this is the reason behind it. So in uses of group 14 elements, nothing too much to discuss. They are important in daily life and industry. Now carbon, how important it is for organic life, we all know this. Then day-to-day life, we are using so many carbon-based compounds, and even in our inside our body, there is so many carbon-based compounds, that is organic. Then silicons, polymers are known by the name polysiloxane. They are used to make lubricant and for vacuum pumps. Silicon and its use, it is also having use in making glasses. Germanium and silicon, they are also used as semiconductor. And the next two elements, tin and lead, used in alloy formation and to make pigments. So once the chemical properties part we have finished, and we have also seen how it reacts, that is how the group 14 elements, they react with oxygen. And we have seen they form two types of oxide. One is monoxide and the second type is dioxide, right? So now these oxides, their property structure we are going to discuss. When it is dioxide, oxides of carbon, that is under dioxide, oxide of carbon means it is CO2. So it will be more reactive compared to SiO2 or GeO2, and these two also having polymeric structure. So to break those polymeric bonds, it is really energy requiring process, but CO2 is gaseous molecule. It is more reactive, fine. Now for monooxides, that is of type EO, where oxidation state is 2+. So these oxides, and that is this type of oxide, except silicon oxide and germanium oxide, other oxides are basically stable, except these two. SiO can exist only at high temperature. Now the first oxide, that is carbon monoxide, it is neutral. That means it will not react with acid, it will not react with base. GeO is acidic in nature, and SNO, PbO, these are also, these are amphoteric. GeO is acidic. Now when you are moving down the group, now gradually it is amphoteric. And SiO is not mentioned here because as we have seen, it is existing only at high temperature. Now for PbO, there are mainly two forms. One form is red form. Another form is yellow form. Same chemical formula, both are PbO. But one form is alpha PbO, which is also called red form because of its color, and the name, another name is used, litharge. The yellow form, it is beta PbO, name is massicot. Now these two forms, yellow form and red form, that is the conversion from massicot to litharge or from litharge to massicot, they can be, it can be done if we control heating and cooling. Okay, so these two forms can be converted to each other. Now for dioxides, now the types will be CO2, SiO2, GeO2. So the first three dioxide, they are acidic in nature. And again, so see SNO, PbO, they are amphoteric, and when it is EO2 type, then also it is amphoteric. Now as the first three EO2, that is CO2, SiO2, GeO2, they are acidic. That means they will react with bases only. And SNO2, PbO2, they will react acid as well as base because it is they are amphoteric. So see, these are the reactions. CO2, it is reacting with sodium hydroxide. It is also reacting with another base, calcium hydroxide. We are getting sodium carbonate, calcium carbonate, SiO2 reacting with NaOH. We are getting Na2SiO3 and GeO2, same type of compound, Na2GeO3. But when we have these two dioxide, now you can see their behavior is amphoteric. So SNO2 reacting with NaOH, reacting with HCl, we are getting Na2SNO3 and SnCl4 respectively. PbO2 also reacting with NaOH, same type of compound, just like tin. Na2PbO3 and with HCl PbCl4. So these two reactions, they are showing the amphoteric nature of SnO2PbO2, and these four reactions, they are showing the acidic nature of the first three dioxide of group 14 elements. The +4 state of carbon is most stable. What it means? It means if you consider +4 oxidation state for this group 14 elements, again I am writing all the elements. So +4 state, it is maximum when we have the first element. And what happens when you move down the group? The tendency for showing +4 state is decreasing and the tendency for showing +2 state is increasing. So that is the reason for Pb +2 is very common, and for carbon +4 is more stable. And why down the group +2 stable? Because of inert pair effect. Now since +4 state of carbon is more stable, therefore among the monooxides, that means if you consider all the EO types, whether it is SiO, GeO, CO, whatever, among all the monooxide, carbon monoxide is strongest reducing agent. So what it means? So carbon, it will always try to move from +2 state to +4 state. So here it is +2, but here it is +4, and it is moving from +2 state to +4 means what? It will lose 2 electron. That means it will act as reducing agent. So when it will act as reducing agent, itself will be oxidized to CO2, but it will donate electron to some other species. So this is CO is showing maximum reducing property if you consider all the different EO for group 14 elements. And because of this reason, carbon monoxide is used in the metallurgy, that is extraction of many metals, where we need some reducing agent, because when we extract metals from ores and minerals, they are in different oxidation states. Suppose the metals are in +2 state, the metals are in +4 state or +3 state. Now we need some reducing agent that can donate electron to these metals, and the metals will be now in zero oxidation state. That means now the metals in metallic state or elemental state, and that is possible with carbon monoxide. Look at these two reactions. Suppose we have this oxide of iron, Fe2O3, and from Fe2O3 now it is converted to zero oxidation state. Similarly, zinc oxide, where it is +2, now it is converted to zero oxidation state. So in both cases, carbon monoxide is acting as reducing agent, and we are getting the metallic form from the oxides, and itself is oxidized to CO2. SnO2, that is tin dioxide, it has very little reactivity, and its reactivity is so little, which is proved by its insolubility in aqua regia. Now what is aqua regia? Aqua regia is mixture of HNO3 HCl, where HNO3 is 1 part and this is 3 parts. That means it is 1:3. HNO3 HCl 1:3. It is also known as king's water, because all the noble metals like platinum, gold, they can be dissolved in this aqua regia. So this is a mixture which can even dissolve gold. But see, SnO2, it's so less reactive that even in aqua regia also, in aqua regia it will remain as insoluble. Fine. Since +2 oxidation state is more stable for lead, that we know, therefore among the dioxide means if you consider all the EO2, then PbO2 will show maximum oxidizing property. Why PbO2 will show? Because when it is PbO2, it is having oxidation state +4, and it will have a tendency to change the oxidation state from +4 to +2. So that is the reason it will accept electron and it will show oxidizing property. Now some examples where it is showing oxidizing property. See, PbO2 when reacts with HCl, the chloride ion which is present in hydrochloric acid, it will be converted to chlorine. That means from -1, now it is converted to 0, and here it is +2, this is +4. So this is reduction itself will be reduced and it will oxidize other species. If you take some other acid rather than HCl, suppose you have taken HNO3 or H2SO4, now what will happen? With HNO3 or H2SO4, now PbO2, it will oxidize the oxide ion that is present in these two acids. So in HNO3 there is presence of oxide, in H2SO4 also there is presence of oxide. Now this oxide having negative charge, see if you look at the right hand side, now we have diatomic oxygen, that means it is zero oxidation state. So here it is -2, now it is 0. So it has lost electrons. So with respect to oxygen, it is oxidation. But with respect to PbO2, here it is +4, here it is +2, this is also +2, lead sulfate and lead nitrate. So PbO2, it will always have a tendency to be converted to the +2 state. It may be, that is in different form. It may be nitrate, it may be PbCl2, it may be PbSO4, whatever it is. But oxidation state, if it can reach somehow +2 state, that means it is reaching the stabler state. +2 state is more stable for lead because of inert pair effect. So based on these oxides, we have a problem. Which of the following is or are not correctly matched? We have total 4 oxide: GeO2 acidic, PbO2 amphoteric, and CO neutral, SiO2 amphoteric. Now this is type EO, this is type EO2, 3 EO2 type, 1 EO type. Now whether it is EO2 type or EO type, we have seen that in case of Pb and Sn, it is always amphoteric. Okay, that means this is true. We have to find not correctly, the wrong one we have to find. And CO neutral, this is fine, this is only oxide which is neutral. But for GeO2 or GeO, in both cases it will show acidity. And SiO2, it is not amphoteric. Amphoteric is only PbO, PbO2 or SNO, SNO2. But not SiO2 is amphoteric. It is actually acidic in nature. But other 3 informations are basically correct. Only 4 is not correct. That means B should be the correct option. It is not correctly matched. All the given oxides, they are amphoteric, except, that means there will be one exception, in which case it will not be amphoteric. Now this same type of same information, basically we have just seen this one is false, that means it is acidic. But here it is mentioned all the given oxides are amphoteric except which one. So this is not acidic. Sorry, this is not amphoteric, this is acidic. But others are amphoteric. PbO2, SnO2, these two are amphoteric, and in group 13 also, that is Al2O3, aluminium is from group 13. There also we have seen, there also we have seen that it is having amphoteric property. So correct option will be except SiO2, rest of the 3 are amphoteric. So we also have one more problem, but we are at the end of the session. So next day we'll finish the rest of the part. Thank you for listening.